get the job done. Okay, so let's try this again. If I want to prove that a sequence converges, right, what's the first line of my... Do I start by writing all this down?
No.
I would not do that.
Let p greater than
Okay. Say it.
Let p be greater than 0.
Let p greater than 0 be given. Okay, don't change it to p over 2 or p over 3 or anything else like that. You always want to just start with a random arbitrary p, just like this. Okay, let p greater than 0 be given. It is now fixed. So I should not see anywhere later in your proof, I should not see this ever written down. Because if I see this written down, it makes me think, oh, now you're talking about all p again, every p. Oh, wait a minute, I've got one specific p right here that I fixed, and that's the only one I should ever talk about, right? So even though we have this for all p greater than 0 in the definition, we're not going to be applying the definition to every p, right? We're only going to apply it to this one p that we have right here and go from there, right? Okay, great. So let p greater than 0 be given. Our job is to come up with a capital M that satisfies our definition for this sequence, right? Would you like me to write down what we need to show, or is it clear to you? You're good?
Yeah.
Okay, I won't write down what we need to show if you don't need me to. It's fine to do it, I just don't want it to... Sometimes it can throw people off. So,
I think it's better to write it. Like,
let me write it over
some
here.
people that don't-
Yeah, let me write it over here. So we need to show there exists an m in the natural numbers such that if n is greater than capital M, then the absolute value of xn plus yn minus x plus y is less than... I'm sorry, not absolute value. I'm using a random metric space here. Sorry, such that if n is greater than m, xn plus yn is an element of the neighborhood of x plus y of radius p. That's the way we want to say it. Okay? So this is for an abstract metric space. There's no absolute value here. Okay, does that look right? Okay. So we have to come up with an m to do our proof. Does anybody have a suggestion what I could do next to sort of start working on the m that I need?
The max of the M1 and M2 in our assumptions. If we elaborate.
So I have some assumptions here, right? And I haven't used them yet. One assumption that I have is that xn converges to x. That means, well, it's right here, for every p, including the one that we fixed right there, I can already find an m. Zane's calling it m1, which is good because it's not actually the m that we ultimately way over there are trying to find. So by assumption, since xn converges to x, there exists an m1 in the natural numbers such that if n is greater than m1, right, then xn is in the neighborhood around x of radius. We can actually, remember guys, for every single p greater than 0, we can find such an m. So I can put whatever I want right in this little space. I'm going to leave it blank for now. Okay? I get to choose what I put here because no matter, basically because xn converges to x, for every radius, this m1 will exist eventually. Okay, so, I mean, you might think I want to put a p here. It turns out it's not going to work. It's going to need to be p over 2. And you'll see why in a minute if you don't see it yet. So I don't know exactly for sure what I want to put there, but we'll come fill that in. Similarly, I want to do a similar thing for the y sequence. There exists an m2 in the natural numbers such that if n is greater than m2, right, y sub n is in a neighborhood around y of any radius that I want. Okay? Yes?
Y
why didn't you put brackets around the yn and the xn? I mean, is that,
This is actually just looking at a specific element at this point.
okay.
Yeah, it's not actually a set, it's just a particular, it's a particular element that belongs to this neighborhood. Okay. All right, so what we're hoping for is to get this point inside of some neighborhood of x plus y, of radius p. By the way, this just means that the distance from xn to x is less than whatever we put into that box. And this one just means that the distance between yn and y is less than whatever we put into that box, right? So just rephrasing it using the metric that we have. Okay? Is everybody so far so good? Okay, so then what you're going to want to do whenever you have two m's, there was one person on the homework, I think, fortunately only one, who used a minimum of these m's. You don't want to do that. It's always, for sequences, guys, it will always be a max. You're going to take the max of these two numbers. Okay? So I'm going to let capital M, this is actually the M I'm trying to find right now. I'm going to let capital M be the max of these two m's that we've already found. And what I'm hoping to do now is show that, okay, really you have to produce this capital M and then check that it works. Okay, so how do you check that it works? You're checking this part. So you're going to now you're going to consider any number bigger than M, right? And what you want to look at is going to be the distance between, so what you're trying to prove is this, right? So you're going to look at the distance between xn plus yn and x plus y. And you need to try to show that that is less than p, right? That is less than p. Does everybody with me?
Yes.
So, what? We do need to choose the specific metric space here.
Yeah.
Because I'm talking about, actually, this is supposed to be, let's just make this the real numbers under the absolute value metric. You could use a different metric space if you wanted. Let's just make it that one. Why am I saying I have to choose that? Well, because normally when you have a metric space, you don't necessarily know how to add points together. So if I got a plus sign in here, then I have to know how to do addition. So I'm just going to measure this distance by using, I love it, you get stuck in the middle of the proof, you just change the question. Please don't do that on the exam. There we go. So we just put that in there. Now that's my metric, right? That's how I measure that distance. And can you tell me what I'm going to want to do with this?
Yeah.
I need to rearrange things a little bit, right? I want to put the x's together. So xn minus x, and then yn minus y. I kind of got to get those terms kind of together, lined up. And now we can use the triangle inequality. So this is less than or equal to absolute xn minus x plus absolute yn minus y. And now you want the final answer here to be less than p. So this is why you want to make each one of these terms less than p over 2. I can go back, if I didn't figure it out before, I can put the p over 2 here, and I can put the p over 2 here, right? So this is the idea, guys. Use a p over 2 for this one. Yes, Sarah?
And we also can use like any fraction for that one, and this one is going to be like 1 minus that fraction, right?
True, true. As long as the two things in the boxes add up
to 1.
to less than p.
Oh, yeah.
Add up to less than p, you're fine, right? So then this is going to end up being p here. So we're done. Does that make sense, guys? This actually, you would have done this in 350. most likely, except you wouldn't have used neighborhoods to refer to it. You would have just used the absolute value metric. So there's just a chance to practice it with the notation that we've been using kind of from this semester. Okay. Everybody okay with that example? Pretty good? Okay, let's do another one. Okay, just practicing these proofs. And remember, guys, it's one thing, watching me do the proof. It's another to do yourself. So be sure that you spend some time also doing some of these yourself. So let's do this, number 4. I'll try to do the harder ones first that I have. Let's assume that G from X to Y is continuous, and H from X to Z is continuous. So these are all just metric spaces. So take two functions like that are both continuous. From one metric space to another, and then the first metric space is the same. The inputs are the same, but they go out to 2 different metric spaces, okay? Then what I'm going to do is I'm going to define F to go from X to Y cross Z. You guys remember this? This is order pairs, right? The Cartesian product of the 2 sets, right? Via, I'm going to give you the formula, via f of little x. I'm going to define it to be, it has to be an output in y cross z. So it's going to have 2 slots, and what I'm going to do is in the first slot I'm going to put whatever g of x is, and in the second slot I'm going to put whatever h of x is. Okay, kind of an abstract example, but this is a way of taking 2 continuous functions and building a new function that has the same domain again, but sort of keeps track of both functions, right? Then what I would like to do is prove that f is continuous. Okay. To prove that f is continuous. So on Wednesday's class, guys, the class last Wednesday, you guys were all there, right? That was like a really important class. And we had like 4 or 5 different things. F is continuous if and only if this thing, and then if and only if something else. It was like proposition 7, 8, 9, 10. Like we had a bunch of propositions, and they're all useful at different times. And the thing that's hard is that they don't tell you here like which way to prove it. We have the definition. Right, so the definition of a continuous function, I know everybody's going to know that on Monday for the quiz. That's the one that says, all right, so for all x in capital X and for all p greater than 0, there exists a q such that if you take a point from the neighborhood of radius q around that point of x, well, the image is within the neighborhood of radius p around f of x. Right? That's the definition. It's kind of a messy definition. So make sure you get that definition exactly right. Make sure you don't have a mix-up with these notations and symbols and so on and so forth, right? It's all very, very, very important to get it exactly right. Anyway, then we also had another one that was pre-images of open sets are open. In fact, when I'm trying to think about continuity, that's usually where my brain goes first. It's so much cleaner than the definition with the P and Q in it, which is kind of a little bit cumbersome. This pre-images of open sets thing, being open, is just very, very, simple to state and remember. And then we had the thing about the sequences. Anytime for a continuous function, anytime you have a convergent sequence on the input side, well, the output, if you apply the function to the sequence, it should converge to whatever the image of the function is of the limit point of the original sequence. So that's proposition 10, I believe. So we have all of these nice ways of thinking about continuity. And we have to sort of pick some kind of an approach here. Does anybody want to suggest what we maybe could do?
So we're gonna to do the rough position. We're gonna use the rough position number 9, right?
Proposition 9, so you're going to take, Proposition 9 is the one that says that the pre-image, for a continuous function, the pre-image of a neighborhood should be open, right? So we would have to take a neighborhood in here, right? So that would be, we'd have to pick a point out of here, and, you know, so we would take, we would be looking at the pre-image under the function of, so don't write this down yet, because I'm just doing some thinking out loud before we write anything too polished down. We would be taking a neighborhood of a point that's in here, let's just say it looks like that, of an arbitrary radius. We would be trying to show that this is open in X. Okay, that would be what we would have to do. So, I guess one of my questions is, what does this look like?
We don't know, because we don't have an actual function.
We don't have a metric.
Yeah, or
Technically, there are metrics here, so I can write d of whatever, you know, there's a distance metric, but you're absolutely right. It's a little hard to know what exactly, how you measure distance in here. I mean, even if it was r cross r, even if that was what y and z are, now you're talking about r squared, and we've seen 4 or 5 different metrics that you can use there, right? You could use the Pythagorean metric, you could use the discrete metric, you could use the max of the absolute differences of the coordinates, right? And so that hasn't been very well explained what the metric is on y cross z. So this is going to be, my problem with using Proposition 9 is great. The challenge with it is to understand what this neighborhood is, what it actually looks like.
I think we're gonna use
I'm
the
going with prop
definition.
10.
I'm sorry?
I think we're gonna use the definition.
The definition. Now the definition also has the neighborhoods in it, right? Because the definition says, you know, for all x in X and for all p greater than 0, there exists a q greater than 0, such that if we take f of any point that is in the neighborhood of x of radius q, it goes into the neighborhood of f of x of radius p, right? So you're looking over here in y cross z at a neighborhood. So it's kind of the same challenge. It's the same problem that we're having with the other proposition. What else do we have?
the other one, we don't know whether or not it's open, so we can't look at the open set and find the pre-image.
Okay, so the graduation question, keep calling it that.
Yeah.
Right, if you start with an open set here, you would need to show that the pre-image over here was still open, right? So that is not a bad thought. The question though is, what does an open set in y cross z look like? You know, one idea, actually this would make a good question also. I could just ask you this. Show that if U is open in Y and V is open in Z, then U cross V is open in Y cross Z. Like you could try to prove some kind of a little statement like that. And that would be true, like this would be an open set in y cross z, but the open sets in y cross z could look even different than that. Like they don't have to necessarily be just the cross product of two open sets in the two spaces. So
And prop 10.
that is also proposition 10. Proposition 10 says,
We need a sequence.
for a function to be continuous, we start with a sequence
X.
in X. So if we started with a sequence that converged, right? So if we assumed this, then we would be trying to show that the sequence of the f of that converged to something.
It's not gonna be that.
I'm sorry, converged to f of x, yeah. Converged to f of x over here, right? And of course, we know that what f of x of n would be. It would just be g of xn and h of xn. And g of xn, remember, g is continuous. So g is going to preserve the image of the limit point to be what it's supposed to be, and so is h. Right? We would actually be able to use that pretty easily. So instead of trying to figure out what neighborhoods in y cross z look like, or what open sets in y cross z look like, right? Which is what you would need to do for the definition, or for Prop 8, or for Prop 9, right? This is the one way of approaching the problem that doesn't require me to think about what neighborhoods or open sets look like at all. So I'm going to propose we try that. Now, if I asked this like on an in-class test, I probably would give you a hint, because there's just too many. You only have an hour and 15 minutes. You can't try everything, If it's a homework problem, it's one thing, But if you're kind of under the time pressure, obviously I'm going to try to, I'm not going to want you to get too bogged down on this. I would probably give you this suggestion. Let's try to use proposition 10. Okay, so solution. We're going to use Prop 10. And to do that, we're going to assume that the sequence xn converges to x. Okay?
Just the one, we don't want to potentially use two.
This is what we're proving. So if you look at proposition 10, to prove that f is continuous, you start with a sequence in the input side, right? And our job is to show, so we need to show that the sequence of the images of those points converges to f of x. Agreed? Okay. Now, since g is continuous, we already know that the sequence of g of xn will converge to g of x. And since h is continuous, if we take the h of xn's, those are going to converge to h of x. Are you guys with me? That's because we're using the continuity of g and h to say that. Okay. So now we need to show that f of xn converges to f of x.
Now we construct our f of x and
Okay, so let's write it down. F of xn is g of xn, comma, h of xn, right? That's the definition of the function. And we already know that the first slot here converges to g of x, and the second slot converges to h of x. So this converges to g of x, comma, h of x, which is f of x. That's it. That's the whole thing. That's pretty much the whole entire thing. So, is everybody comfortable that if the first slot converges to the first slot and the second slot converges to the second slot, then this pair converges to this pair? And it's basically what we're saying right there. So that's it. So it works pretty easily in this case to use sequences to kind of show that. It's kind of a nice little result. Okay. Let's see what else I want to do. Oh yeah.
But the trick is specifically, like it could have converged to a lot of things, but specifically choosing g of x and h of x is one thing it work. Like,
Well,
it
we
could-
know that we know that xn is converging to x, so g of xn has to converge to g of x, right? We're not choosing that. That is what it converges to. And h specifically is continuous, so again, just applying h to both sides of this convergence preserves the continuity. So guys, when a function is continuous, what it means here is that you can apply the function to a sequence and it goes through the convergence on both sides. That's what it means.
And that was also because both of those functions started in x.
Yes. Well, I actually originally was going to do a different example, but yeah, this is a little easier to have just one input here. So you take any input from x and then you spit out two different things depending on the g and the h. Yeah. So that's a nice little example, just to practice that proposition that we had. Okay, let's do another one. Number 5. Now we're going to get down to the ones that go faster. This won't take us too long. At least I think they're going to go faster. Okay, so let U be open in X and let capital F be closed in X. Okay? So you take one open set and you take one closed set. And what I want to do is prove two things actually. I want to prove that U minus F is open in X. And then I also want to prove that F minus U is closed in X. I'm going to do it both ways. So if you start with an open set and you subtract a closed set from it, it stays open. Or if you start with a closed set and you subtract an open set from it, it stays closed. Okay, so let's start with part A. I want to show that U minus F is still open in X. And I'm wondering what you think. I've made this problem so abstract to try to discourage you from using neighborhoods and metrics and all that stuff. You could say, well, there's got to be a metric. I could find a P and blah, 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 blah. It's going to be very messy. We can probably get away with something a little easier. Did you have an idea?
Well, I drew a picture, and from what I understand, if you have a big set X, yeah, thank you.
Uh-huh.
And then you
You
have
can
an
come and
open,
draw it if you want. Or, well, you can just describe
just
it.
a dotted circle U.
Okay, I like
And
that.
then I put F a little bit over U.
Kind of like this.
Yeah.
Okay.
And then I thought,
Including the edge of it.
right. So if we have
So
U.
U
is-
minus F is going to be here.
Right. But U was already a union of neighborhoods without F.
Mhm.
So then we can still make all of those sets unions of neighborhoods in there. I mean,
So the part that's shaded is really a union of neighborhoods and therefore open.
Right.
Absolutely true. That's absolutely true. So we could do that. We could just say take every single point out of U minus F, right? We can build a neighborhood around it, right? And then take a union of all of those. Exactly. There's a little bit shorter way to basically get to the same conclusion. That will work. There's nothing wrong with it, but does anybody have maybe just a slightly, faster?
Can you rewrite that as intersection of U and X minus F?
Yep, that's what I was looking for. So, if you want to know what your set actually is, what is this shaded region, right? It's the stuff that's inside of the dotted circle, but outside of F.